Today you can see that we're into lesson 6.2. We'll be talking about the normal distribution. It's also referred to as the bell curve. The standard normal curve is another name that is given to this. We learned in a previous lesson about the distribution of data, and that the distribution of data measures the frequency with which each data point occurs. And we looked at a frequency table, for example, back in lesson 6.1 to help us kind of organize, especially when the data points become quite large. Well, we're going to see today that the normal distribution is a specific distribution that will illustrate for us in terms of standard deviations how far our data points are clustered in relation to the mean. And we'll see that in specific form on the next slide. But first, let's just go ahead and fill in some blanks. If data are truly normally distributed, their graph is a bell, as we mentioned before, a bell-shaped curve, and you can see an example here on this slide. The mean and the median are the same. All right, so using our example here, the median is this the number that is represented by this red line, the very center. And we usually use the word median to refer to the center, but that's also going to be the mean for this graph. Most of the data tend to be clustered relatively near to the mean. You'll see in just a minute specifically what percentage of the data is within one standard deviation of the mean. And the data are symmetrically, there's symmetry here. This line is like a line of symmetry. It is. It splits this data, this bell shape, into two equal halves. So the data are symmetrically distributed above and below the mean. So above would be to the right and below would be to the left of the mean. All right, so let's dive in a little bit more. Mean and standard deviation for the normal distribution. We said a minute ago the mean determines the middle of the bell curve, so that's where the curve peaks. All right, so this number right here would represent the mean, also the median. The standard deviation determines how steep the curve is. So we'll go back to our previous slide. A steep bell curve would mean a smaller number for the standard deviation. So the smaller the standard deviation, the steeper the bell curve would be. And in contrast, if the standard deviation is a larger number, then it's going to be a wider bell curve. All right, so here are some rules of thumb. This is describing some people refer to it as the 68, 95, 99.7% rule. I'll illustrate why in just a second. It's also known as the empirical rule. So you might see that language referring to what we're about to do. 68% of the data lie within one standard deviation of the mean, 34% above and 34% below. So using our picture here, we could fill in this area. This represents a total of 68% of the data will fall within one complete standard deviation of the mean. And as the rule of thumb says, you can basically split these up into two 34% areas each. Remember, there's symmetry with this line. And then broadening out to two standard deviations, we would include the 95% of the data. So if you think about it, 95 minus 68 is 27. So we're going to take that 27 and basically divide it up, and we'll put 13.5 on the left below the mean, and then 13.5% on the upper side. So right in there we have 95% of all of our data that's been collected would fall within two complete standard deviations of the mean. And then to make up the 99.7, you can see that that's 4.7. So that's going to be, just breaking up the 4.7, that's 2.35% below in that small area, and then 2.35% here. So that's what we mean by the 68, 95, 99.7% rule. All 99.7, it's not 100%, but 99.7% of all the data that has been collected should, if it's normally distributed, will fall within 3 standard deviations of the mean. All right, so with that being said, let's take a look at some applications of the standard normal curve. So adult male heights are normally distributed with a mean of 69.1 inches. The standard deviation is 2.65 inches. So what does the 68, 95, 99.7 rule tell us about the height of adult males? All right, so let's just say within 1 standard deviation of the mean. All right, so we could say the mean would be here, 69.1. All right, and if I go to the right, 1 standard deviation, all right, add those two numbers together, that would be 71.75 inches. And if I went to the left, that would be starting at the mean and subtracting 2.65. That would be 66.45 inches. So we could summarize by saying 68% of males fall between 66.45 inches in their height and 71.75. 66.45 inches and 71.75 inches. All right. And now going out to 2 standard deviations of the mean, so you could think of this. You're going to add 2.65 times 2, and then you would subtract, starting with the mean, and subtract 2.65 times 2. That would get you the numbers that represent the upper and the lower range of 2 standard deviations. So going to the right, that would be 74.4 inches. And then to the left, it would be 63.8. And so we'll make a statement that 95%, we're within 2 standard deviations of the mean of males, are between these 2 heights. 63.8 inches tall and 74.4 inches tall. And then finally, to get our final, the 99.7%, we would do this one more time, but we're going to go out 3 standard deviations from the mean. So we would do 2.65 times 3, and then we would subtract 2.65 times 3. Going to the right, that would be 77.05, and then to the left, 61.15. And then you would say, finish that off with 99.7% of males are between those 2 measurements. 61.15 inches and 77.05 inches. Okay, here's another example. So here you would start with the mean of 64.1. And just following our previous example, to get 1 standard deviation of the mean, you would add 2.5. That would give you the upper limit. You would subtract 2.5 for the lower limit. So I'll just go ahead and summarize this. So 68% of women are between 61.6 inches and 66.6 inches. All right, 64.1 plus 2.5 and minus 2.5. And then the next set that's within 2 standard deviations of the mean, that would represent 95% of women And so now you're doing 64.1 plus 2.5 times 2, it's just times 5 really, and then minus 2.5 times 2. So those two values representing that range would be 59.1 inches and 69.1. And then the final 99.7% of women, we do go out to 3 standard deviations, and we would have these numbers representing the range. We would be between 56.6 inches and 71.6 inches. All right, so that's an example of something you'll be doing on your assignment, where you have to show your knowledge of this empirical rule. Okay, now let's use the empirical rule to actually count a number of items. All right, so the weights of apples in the fall harvest are normally distributed. We have a mean of 200, so just do a little visual here. A standard deviation of 12, so you might consider this. I'm not saying this is required, but just to give us something to look at. As I go to the right, I'm adding 12 just to get the number line picture, and then as I go to the left, I'm subtracting 12. All right, and so this represents 34% and 34%. This is another 13.5% on either side. So now that I've got this to look at, the question is how many apples will fall in their weight between 176 grams, which is here, and 224 grams. So that represents 95% of all of the apples. So I have a supply of 2,000. I multiply by 95%, and that's going to give me a total of 1,900. Okay, we'll do another one. The weights of oranges are normally distributed, a mean of 220, standard deviation of 35. So you could do this little sketch. 185. And I think we've gone far enough because they want us to tell how many of these 4,000 are between 185 grams and 255 grams. So this is our mean. So this represents 68%. Remember, there's 34% on either side within one standard deviation. And that's what this represents within one standard deviation. So I take the 4,000 oranges and I multiply by 68%. And I get 2,720. Okay, moving right along, let's talk about z-scores. You'll be using the z-score formula quite a bit in the assignment that you'll be doing following these notes. So let's take a look at the z-score formula. Basically, the z-score is a way for us to determine how far a data point is from the mean, but instead of counting literal data points, I'll use this example. Instead of saying, for example, that 290 is 70 data points from the mean, the z-score would say it's actually 2 standard deviations above the mean. So it's a way to count how far data is from the mean, but we're counting in terms of the number of standard deviations. And a plus would mean it's above the mean. A negative z-score would mean it's below the mean, whatever that number is. Okay, so let's see how it's calculated. Instead of saying that an SAT score is 111 points above the mean of 507, you could say that the score is 1 standard deviation above the mean. Okay, let's just do an example. The weights of newborns in the U.S. are approximately normally distributed. The mean is about 3,332. The standard deviation is 530. Calculate the z-score for a newborn weighing 3,700 grams. Okay, so in our formula, the data point is going to be this 3,700. The mean we were given is 3,332. And then we just divide by the standard deviation of 530. Just a reminder, if you do all of this in your calculator, you'll want to put parentheses around operations like subtraction. So we go to our calculator and we end up, and these are typically, as the notes tell you, we will typically round z-scores to 1 decimal place. So that's going to be negative 0.7, or positive 0.7, sorry. All right, now let's do another example. If the newborn weighed 3,000 grams, so that's our data point, mean divided by standard deviation. And this is going to fall below the mean. Negative 0.6 would be the z-score. Okay, percentile scores. So percentiles, the percentile for a number relative to a list of data is the percentage of data points that are less than or equal to that number. Maybe you've heard this come up in the context of standardized test scores, where maybe you were told that you scored in the 88th percentile. Well, what they're saying is that's pretty good. Relative to everybody else that took that same test, you scored better than 88% of everybody else. Okay, so you're above, in other words, you were at the top of 88% of all the other students. 88%, in other words, fell below you in their score. So that's what percentiles are all about. And this table 6.2 that's provided in your text is going to be huge, because we're going to be able to, once we find a z-score, we'll be able to look up that number and be able to determine the percentile score. So this is going to use the z-score formula. So let's take a look at example number 7. The average length of illness for flu patients is normally distributed. There's a mean of 8 days and a standard deviation of 0.9. What percentage of flu patients will be ill for more than 10 days? Okay, so keep that in mind, because percentiles are all about, when we find a score, that represents the percentage of people below. That would be less than 10 days. So how do we account for the fact that they're wanting the percentage of flu patients that will be ill for more than 10 days? All right, first let's find out what the z-score is. So we take our data point, which is 10. We subtract the mean, which is 8, and we divide by the standard deviation. And that gives us a z-score of 2.2. All right, now you're going to go in your text and you're going to look up the table on page 29. So if you need to pause and go back in your text portion and look at this table, you'll see it's pretty large, and you're given percentages, percentile scores, and z-scores. Let's just take a look. If we look up a z-score of 2.2, turning to the table, you will see a percentile score 98.61, but we will just round that to 98.6. Okay, so let's put in context, what does that 98.6% mean, that percentile score? Well, this would be the percentage of patients that will be ill for 10 days or less. or you could say they'll recover within 10 days. But 10 days is the maximum, the length. 98.6% will be ill for a maximum of 10 days or fewer. Okay, remember that, less than or equal to. So we want the number, the percentage that will be ill for more than 10 days. All right, so we're going to have to do 100% and subtract off the 98.6 to give us the number that would be ill for more. All right, so when you get a percentile, you're always thinking that is less than or equal to a given number. And when you're asked to find greater than the number, you'll have to do this little subtraction exercise. Okay, let's do another example. Using the preceding information, what percentage of flu patients will recover in 7 days or less? All right, so now 7 is our data point. 8 is our mean. We still have the same standard deviation. So we get a z-score of negative 1.1, and this is what percentile scores are all about, 7 days or less. So this time we're not going to have to do any subtraction. We just look up the z-score and that percentage, and we'll round these to the nearest tenth. So that would be 13.6% of flu patients will recover in 7 days or less. All right, here's another one. The weights of newborns in the U.S. are approximately normally distributed. The mean birth weight is about 3,332. Standard deviation is 530. What percentage of newborns weigh more than 8 pounds? So we got to find the z-score. All right. So once again, 8 is our, sorry, not 8 pounds, the grams. So 3636.4 is our data. The mean is given. Standard deviation is given. All right, and so this gives us a z-score of 0.6. And looking up 0.6 and its related percentile score, that would be 72.6%. Well, that would be the percentage that weigh 8 pounds or less. So we're going to have to do that subtraction deal here again. So we're going to do 100% minus the 72.6. And so our answer here is going to be 27.4%. Okay, let's try another one. Low birth weight is a medical concern. The AMA defines low birth weight to be 2,500 grams. What percentage are classified as low birth weight? So this time our data point is 2,500. We still have the same mean of 3,332, same standard deviation. The z-score is going to be negative 1.6. So we go to our table 6.2 and we look up z-score negative 1.6, and that's 5.48. And because we are looking for lower, that weight or lower, then we can actually use this percentage rounded to the nearest tenth, and that's 5.5%. All right, let's move on to the central limit theorem, and we're just about to the end of our notes. The central limit theorem basically says percentages obtained by taking many samples of the same size from a population are approximately normally distributed. The central limit theorem is a way for us to derive the standard deviation if we're given the sample size and we're given the mean of the population. So notice here that P in these problems, the mean, it's going to be given as a percentage because we're taking samples of a whole population. But when we use the number in the formula, we just use the regular number. So not 0.30, we're just going to use 30 in place of P. All right, so let's find the mean and the standard deviation for this particular situation. A certain disease, 30% of untreated patients can be expected to improve. So that's the sample sample size, or the sample that was collected, and that represents our mean. So we can go ahead and answer that pretty quickly. We observe a population of 50 patients and record the percentage of who improves within a week. According to the central limit theorem, the results of this study will be approximately normally distributed. So we're supposed to find the mean, already done that, and then the standard deviation. So that's where our formula is going to come in. So it's going to be the square root of P is the mean, but as a whole number, 100 minus P, and then N represents the sample size, which in this case is going to be 50. All right, so we go to our calculator, and the square root of this fraction, and you can try this out, is 6.5, and that answer will be as a percentage. All right, and we're rounding to 1 decimal place. Okay, let's try another couple. Find the percentage of test groups of 50 patients in which more than 40% improve in 1 week. So let's do our z-score formula. This time it's going to be 40. All right, 40 minus 30. Okay, the value, the data point, minus the mean, divided by the standard deviation. We found that on the previous slide. All right, and that gives us a z-score of 1.5. We go back to our table, 6.2, back on page 29, and we look up the percentile score for a z-score of 1.5, and that's 93.32. But this is more than 40% will improve. The 93.32 would be 40% or less. So here again, we have to do the subtraction. So 100 minus 93.3, and that gives us 6.7%. Okay, let's try one more. On your campus, 20% of the students are education majors. All right, that's going to be the mean. Suppose you choose a random sample of 75 students and record the percentage of education majors. All right, so let's find the standard deviation according to the central limit theorem. So it's 20 times 100 minus 20 divided by the sample size, which is 75. So in your calculator, doing that calculation, you should get 4.6%. All right, now we're going to use this. We'll be able to use this information to find a percentage of randomly selected groups of 75 students that will include 10% or fewer education majors. So we're trying to get back to the table 6.2 to look up a percentile score, but we need a z-score to make that happen. Okay, so our data is the 10% minus the mean, which we calculated above, which is 20%. Just put them in as whole numbers, divided by the standard deviation, which we calculated earlier as 4.6. So that's a z-score of negative 2.2. We go to table 6.2 and we look up negative 2.2, and it's rounded to nearest tenth, it would be 1.4. And the 1.4% does include, it describes 10% or fewer, so there's no need to do the subtraction from 100 in this case. All right, I think that takes care of our notes. I think you are ready now to do some practice problems. I hope this helps. If you have any questions about this lesson, please let me know, and I'll see you next time.